So, next question. F of z is equal to z minus I capital L log of z squared plus 1. Question is, where is f continuous? And after we've done that, can we extend the domain of f? Can we give f values at some point where it's not defined by this definition in a way that is continuous? So, let's start out. First of all, when is f defined? The domain of f, well, this is always defined, but log is not defined when its argument is 0, so this expression is not defined when z squared plus 1 is equal to 0, or when z is equal to plus or minus I. So the domain is all of the complex plane, but I have to exclude the points plus or minus I. So we don't have to worry, at least when we're trying to work out whether f is continuous enough, we don't have to worry about plus or minus I because it's not defined there, and therefore the question of whether the limit as z approaches plus or minus I is equal to the value of f at plus or minus I is not a relevant question. So, where is f continuous? Well, z minus I is continuous, so it's really related to where log of z squared plus 1 is continuous. Now, log is continuous on the complex plane, but I have to get rid of the negative real axis. So this is where log is continuous. So this will be continuous as long as z squared plus 1 is not in the negative real axis. So z squared plus 1 is equal to, let's say, minus t, where t is a real number and t is greater than or equal to 0, means that z squared is equal to minus 1 minus t, or minus 1 plus t. So here I have a real number that's greater than or equal to 1. Z squared is that. That says that z is equal to plus or minus I times y, where y is greater than or equal to 1. Actually, we better say that z is equal to iy, where the modulus of y is greater than or equal to 1. So y here is a real. This is the x plus iy. So on this part of the imaginary axis between minus I and I, here it is continuous, but at these points it's not continuous. Now, that's where log is not continuous, and I guess that we can say where log is continuous, then f is also continuous. But we could also say where f is continuous, then f divided by z minus I will also be continuous, which would say log is continuous. That means that we can say that f is not continuous here. And here, and it is continuous everywhere else. Now, let's answer the first bit. Can we extend f? Well, first of all, what happens when the z, I guess the only points where f is not defined at the moment are minus I. Now, the limit as z goes to minus I of z minus I times log of z squared plus 1 is actually infinite. Why is that? Well, this is going to go to 2i. If I take the absolute value of this, then this is going to go to 2. When I take the absolute value, I'm going to have an ln of mod of z squared plus 1 plus I arg of z squared plus 1. And as z goes to plus or minus I, then this is going to go to infinity. So this bit here goes to infinity. This stays between, well, the argument itself stays between pi and minus pi. The fact is that this is bounded and it can't stop this part here going to infinity. So the limit is indeed infinity. So we really cannot extend f at this point. However, now I look at the limit as z goes to I of z minus I log of z squared plus 1, which I can write as a sum of three pieces. Z minus I ln of mod z minus I, z minus I ln of mod z plus I, and z minus I times the I times the arg of z squared plus 1. So I've taken the log of z squared plus 1, I've written that as ln of mod of z squared plus 1, which I can then break up into these two pieces, plus I times the arg of z squared plus 1. And there is, of course, a z minus I in all of these. Now, the second one, as z goes to I, this goes to 2I, so this goes to ln of 2, and this goes to 0, so this one goes to 0. This one here, well, the arg is always the modulus of I times z minus I times the arg of z squared plus 1 is always less than or equal to pi times mod of z minus I. As z goes to I, this goes to 0, so this goes to 0, and so this one is also going to 0. So these two go to 0. Now what about this one? Well, if I look at the modulus of this one, I might as well be looking at the modulus of z minus I times ln of mod z minus I. And if I call this r times ln of r, then I'm looking at what happens to this as r goes to 0. Now, it's an exercise from first year calculus to show that the limit as r goes to 0 is then positive of r times ln of r, which can be written as ln of r over 1 over r. And now using L'Hopital's rule, I get a 1 over r and minus 1 over r squared. And this, when I multiply that, is actually minus r. So this is equal to 0. So coming back here, this goes to 0. This third part here also goes to 0. And so the limit as z goes to I and z minus I log z squared plus 1 is also equal to 0. And so in much the same way as before, I can let f of I equal 0, and I have extended f continuously to that point. And that's the end of the story.